Before we move on to the kinetics of rigid bodies, we need to first talk about mass moment of inertia concept. This is important to understand the rotational motion of rigid bodies and the kinetics equations derived as a result of these rotational motion. Now, the rotational equation of motion of rigid bodies contains this property called moment of inertia. We're going to talk about this as it is applied for three-dimensional rotations as well, but at the moment we will keep it simple to understand the concept and talk about the mass moment of inertia, which is usually identified with this letter I. And sometimes we have these subscripts, especially if we are going to talk about some three-dimensional motion, and then we are trying to use a specific moment of inertia, mass moment of inertia of that three-dimensional motion. But at the moment, I is just enough for our case, so we're going to use I. And what this really means is that there is this finitely small amount of mass dm, and then this dm has this rotational motion, and there's this angular acceleration alpha, and r times alpha is actually represents its acceleration. Okay, this let's say body is doing a fixed axis rotation, and the axis is defined by this OO line, and along this line, about this line, this rigid body rotates. And then at an r distance, there's this finitely small amount of mass dm. The acceleration it experiences is due to this alpha angular acceleration and this r distance. So r alpha in that case becomes our acceleration. And now if we remember our F equals ma case, now m is dm times a in this case would be the force acting on this, would be equal to the force acting on this, let's say, mass. Now, if we're going to talk about the moment about this axis, or you can say about this point for this specific mass, but we are considering this axis, so there could be masses at different locations. So this is the moment about this axis. Then we're going to use the same r information again. So what we need to do is df times r would be, in that case, equal to r squared alpha times dm. And this is actually equal to the moment. Now, if we integrate this over the total mass of this rigid body, then at one part of the integration, we receive this information as I about O. So we need to specify the location of it by the subscript. This is about the axis OO times alpha. And here, this IO is represented by this calculation, integration of r squared times dm. And we call this mass moment of inertia about the axis OO, because about a different axis, obviously this r distance will change, so it will be a different type of information. Okay, so you need to specify about which axis it is, and thus we have this information of this subscript as O. So in the subscript we have about which axis we are taking this mass moment of inertia. There's the information about the mass. That's why we call it mass moment of inertia, because of this dm. It is called mass moment of inertia. Actually, you kind of remember this as we already talked about the first moment about the mass center, right? The first moment about the mass center of a rigid body is equal to 0, right? Do you guys remember that? Now, this is the second moment, but this is the second mass moment about the mass center. If you're going to use it as a mass center, then it will be the mass center, but it's not going to be equal to 0. It will be, if you're going to do this calculation about the mass center, then it will be the mass moment of inertia calculated about an axis in the mass center. And you would call it IG probably in this case. So this is the origin of this information of mass moment of inertia. Now, if we imagine that all the mass of this rigid body is concentrated at a kappa, this is kappa, it looks like K, a kappa distance away from the axis. So we have this axis, and then all this mass, you can think of it kind of like a very thin ring, and all this mass is concentrated on this thin ring. And if this radius is kappa, then this mass moment of inertia is defined by kappa squared times m. Kappa again is the radius of this total mass of the rigid body, the location of that rigid body with respect to the desired location that we want to do this calculation. So I here the mass moment of inertia is calculated by using this kappa information, and the kappa is named radius of gyration. So if kappa information is given to you and then the mass information is known, then you can find the mass moment of inertia defined for this kappa. For a different location, the kappa information would be changed as well. So it's kind of like the representation of this rigid body, which has a different shape, in terms of a very thin ring with a radius of kappa. And all the mass is on this thin ring. And by using the same type of information, actually we can derive this equation to find the radius of gyration kappa as the square root of moment of inertia over the mass. This is an important property that we're going to use later in our studies about kinetics of rigid bodies. Now, another important concept is the transfer of axes, which is also known as the parallel axis theorem. We can have the information about a specific axis. Let's say that we already derived this information about point O, which passes through this mass center at G. But then we are interested in finding this mass moment of inertia at a different location, at a different axis, which is actually parallel. These two axes are parallel to each other. A classical problem about this is in robotics. For example, if you have a single link, a rotational link like that, and then this link is a bar, which is a rigid body, and its mass center is around here, and then you kind of calculate the mass moment of inertia with respect to the axis going out of the board, but at this point of the mass center. Okay, so IG is calculated there, but then you're interested in finding the amount of torque that you need to apply here to rotate this rigid body. Now, for that, this torque or the moment is equal to, now if we call this location O, IO times alpha, but we don't know IO. That's something I need to find out. Or I could have calculated this in a different way. I could have said that this tau is actually equal to IG times alpha plus, if I say there is this mass, this total mass of this bar is m, then it will be m times, if we call this distance, let's say L distance, or it is called D, so let me just call it as D, from the rotation axis to the mass center, let's call that D, m times alpha D is the MA, right? Alpha times D is the acceleration. If I multiply this one more time with D, then it becomes the moment due to the acceleration of this mass. This is the linear part, and this is about the rotation. So in total, actually, we have proved at the moment this transfer of axes. So as a result of that, if I combine these two information, what I get is IO is actually equal to IG. And in order to do this, what I do is I keep this alpha out of the equation. So there's this parentheses of IG plus MD squared. So plus MD squared. And there is the other way of proving the same concept of parallel axes. So if you want to move this information of the mass moment of inertia from the mass center, let's say, to a different location, which is again about a parallel axis, then you use this distance information and then multiply the square of that distance information with the mass of that rigid body. And this is called the parallel axis theorem. Parallel axis theorem, and this is the main formula for this parallel axis theorem. We have IC here. I wrote it with O, doesn't matter. I used O here in this figure. C is used, that's why there is this C subscript here. So as a matter of fact, then if you take a look at this equation closely, the mass moment of inertia that is going to be calculated anywhere other than the mass center would be a higher mass moment of inertia, because you're going to have always d as a square, and this is a positive value here, and as a result of that, the resultant, the new mass moment of inertia that you calculate at a different axis, let's say this axis, will still be more than the mass moment of inertia that is calculated about the mass center. It's an important issue that you might use in your engineering calculations as well. So as a result of that, if you want to minimize this torque that you're going to apply for this joint, for example, while rotating this part, probably you would like to move this mass closer to the rotation axis, because at the end of the day, the mass moment of inertia that is going to be used in finding this torque is found by squaring this distance. If you make this distance smaller, then the amount of torque that you're going to spend for rotating this bar will be also smaller.